In the past few years, artificial intelligence has transformed from a niche research field into a foundational technology reshaping industries, workflows, and the very way we interact with machines. At the heart of this revolution lies a class of models known as large language models, systems capable of understanding, generating, and reasoning about human language at an unprecedented scale. But how do these models actually work? What enables them to mimic human-like comprehension and creativity? And what happens under the hood when you type a simple prompt like, "Explain quantum computing like I'm 5? To answer these questions, we need to dive deep into the architecture, training process, and mechanics of modern large language models, starting with the most fundamental building block, the transformer. The transformer architecture, introduced in 2017 by Vaswani et al. In the paper, "Attention is all you need," marked a turning point in natural language processing. Unlike earlier models based on recurrent neural networks, RNNs, or convolutional neural networks, CNNs, transformers process entire sequences of text in parallel, making them vastly more efficient and scalable. This parallelization is achieved through a mechanism called self-attention, which allows each word in a sentence to dynamically weigh its relationship with every other word. Let's unpack that. Imagine you're reading the sentence, "The cat sat on the mat and the dog barked at it." When the model processes it, it must determine whether it refers to the cat or the mat. Traditional models might rely on fixed positional encoding or sequential scanning. But with self-attention, the word "it" computes a weighted sum of all other words in the sentence, assigning higher importance to mat because of semantic context and proximity. This dynamic, context-aware weighting is what gives transformers their remarkable ability to capture long-range dependencies. Each self-attention layer operates through three key components: queries, keys, and values. Think of them as a search system. The query is what you're looking for, say, the meaning of the word "it." The key is a representation of each word in the sentence, used to match against the query. The value is the actual information associated with each word, its meaning, role, or embedding. The attention score is computed as the dot product between the query and each key, scaled by the square root of the key's dimensionality. This score determines how much influence each value should have on the final output. After computing these attention scores, a softmax function normalizes them into a probability distribution. The final output is a weighted sum of the values, where words with higher attention scores contribute more. This process is repeated across multiple attention heads, typically 16, 32, or even 64 in larger models, each capturing different types of relationships: syntactic, semantic, or even pragmatic. Now, once the self-attention layer has processed the input, the output is passed through a feed-forward network, a simple two-layer neural network with a nonlinear activation function like GELU. This network applies transformations to the attention output, allowing the model to learn more complex representations. The entire block, self-attention followed by the feed-forward network, is repeated across multiple layers, typically 24 to 100 or more in state-of-the-art models like GPT-4 or Llama 3. But how do these models learn? They're trained on massive datasets, often hundreds of billions of tokens, collected from the internet, books, scientific papers, and code repositories. The training objective is simple in principle: predict the next word in a sequence. Given a sequence of words, the model outputs a probability distribution over the entire vocabulary. The goal is to maximize the likelihood of the correct next word. This process is called autoregressive generation. The model generates text one token at a time, feeding its own output back into the input for the next step. For example, if you prompt it with "the sky is," it predicts blue with high probability, then the next input becomes "the sky is blue," and it continues. This iterative process continues until a stopping condition, like a special end-of-sequence token, is reached. But training a model on raw text isn't enough. To make it more useful, especially for tasks like answering questions or following instructions, models are fine-tuned using a technique called instruction tuning. Here, the model is trained on pairs of instructions and desired responses, such as "summarize this article," paired with a concise summary. This teaches the model not just to predict the next word, but to follow instructions, reason step by step, and adapt its tone and style. Even more powerful is a method known as reinforcement learning from human feedback, RLHF. In this approach, humans rank multiple model-generated responses to the same prompt, and the model learns to favor responses that humans prefer, those that are more helpful, truthful, and aligned with human values. This creates a feedback loop where the model improves not just in accuracy, but in alignment, making it more useful and less likely to generate harmful or misleading content. So how does all this translate into real-world performance? Consider a model like GPT-4. It might have over 1 trillion parameters, each a learnable weight in the neural network. These parameters are adjusted during training to minimize prediction error. But the real magic isn't just in the number of parameters. It's in how they're organized, how the attention mechanisms allow the model to focus on relevant information, how the deep layers build increasingly abstract representations, and how the entire system learns to simulate reasoning. For instance, when asked to solve a math problem, the model doesn't perform actual arithmetic. Instead, it simulates a reasoning process by generating intermediate steps. First, identify the variables. Then apply the formula, as if it were thinking through the problem. This is called chain-of-thought prompting, and it dramatically improves performance on complex tasks. But let's be clear, these models don't understand in the way humans do. They don't have consciousness, beliefs, or subjective experience. They're statistical pattern matchers, extrapolating from vast amounts of training data to generate plausible continuations. The illusion of understanding comes from their ability to capture subtle linguistic regularities and contextual dependencies across millions of documents. And yet, their capabilities continue to grow. Recent advances in model efficiency, like mixture of experts architectures, where only a subset of parameters are activated per input, allow models to scale without a proportional increase in compute. Techniques like quantization and distillation enable smaller, faster versions of large models to run on consumer devices. What's also emerging is a shift from pure language modeling to multimodal reasoning. Models like GPT-4 can process images, audio, and text together, enabling them to describe scenes, answer questions about visual content, or even generate code from diagrams. This convergence of modalities is opening new frontiers in AI-powered tools for education, healthcare, design, and beyond. So where does this leave us? Large language models are not magic. They are complex systems built on decades of research in machine learning, neuroscience, and computer science. They reflect the data they're trained on, both its richness and its biases. They can be powerful assistants, creative collaborators, and analytical tools, but they are not infallible. The future of AI lies not just in building bigger models, but in making them more reliable, interpretable, and aligned with human values. Researchers are exploring ways to audit model behavior, verify reasoning steps, and integrate external knowledge sources. The goal is not just to generate text, but to generate insight. As we continue to push the boundaries of what machines can do, one thing remains clear. The most powerful tool we have isn't the model itself. It's our ability to understand it, question it, and use it wisely. Because in the end, AI isn't about replacing human intelligence. It's about amplifying it,